Hello, everyone. I'm Jicheng, an assistant professor from ShanghaiTech University. My current group focuses on aerosol nanotechnology to develop the future of system-level integration and advanced printing solutions. Aerosol usually gives the first impression of smoke, while we transform this stereotype into powerful nanomanufacturing technologies, so that we can create new materials to explore and to invent novel functionalities. Today, I'm mainly focused on the use of spark mashup to create alloys that are not accessible by any other method. Part of this work was finished during my stay in Seoul National University, South Korea. As we already know that there are many challenges in manufacturing alloys. The major challenge is to have a mixed source that can also be kept to the final alloys. For alloy development, it is mainly based on traditional liquid and solid transformations. And in this transformation, there is inevitable interplay between kinetics and thermodynamics. This also complicates the situation to keep an already mixed state to the final alloys. Because of all these factors, very limited range in the phase diagrams have been explored, and therefore there are many new possibilities for materialization. This slide shows that the two paths to form crystals, one is passing a liquid state, and the other is not. Path 1 allows trapping the liquid state to amorphous, while path 2 provides a direct vapor crystal transformation. In this talk, we will show you that the vapor crystal transformation is proven to be the most efficient kinetic pathway for forming alloys, including some ones that were not available before. Next, I will show you a vapor source technology called spark discharge, which we sometimes also call it artificial lightning. We, however, place this artificial lightning into a gap between the two electrodes. And through this gap, we flush an inert gas. The ignition of the lightning, we have to rely on the resistance, inductance, and capacitance circuit, which we also call it RLC circuit. We can see that there is a constant current source which charges the capacitance when the voltage over the capacitance reaches a breakdown, a discharge forms between the two electrodes. The electrodes can be made out of the same materials or different materials. For example, they can be made out by metals, alloys, or semiconducting materials. After discharging, the next charge also takes place again, and then followed by discharging. This is the so-called self-charging and discharging process, and it forms a spark discharge like here, with a frequency about several hundred hertz. Here the time scale is milliseconds. If we zoom in the peak voltage here, the single spark discharge oscillates within a few microseconds. Later, I will explain the use of this oscillatory spark for mixing the materials that do not like each other. This technology forms a short, pulsed spark, which is actually a micron-sized plasma channel. The plasma temperature can be as high as 20,000 Kelvin, thus easily vaporizing the electrode materials. The vapors are then rapidly quenched to form very small nanoparticles down to a few atoms up to a few nanometers. For these, with a few atoms, they are known as atomic clusters or superatoms. Due to this rapid quenching, there is a very, very high supersaturation that pushes the critical nucleosides down to atomic range. Based on this simplification, we developed both analytical and numerical models to predict the collisional growth of the nanoparticles. From these models, we learned that the particle size is controlled only by the electrical parameters and gas flow rate. So the electric parameters are spark energy E, spark repetition frequency F. Besides the size control, This technology also gives unlimited possibilities. We can mix the materials both at the atomic scale and the nanoscale. The atomic scale mixing is for making alloys, and the nanoscale mixing is for particle-particle mixing. Here, we show 3 different electrode configurations: alloyed electrodes, compacted electrodes. Both configurations are made the same materials. And the third one is the electrode is made from different materials. The first configuration uses alloy electrodes to make alloy nanoparticles that retain the composition of the parent electrodes. There is a difficulty to obtain the alloy electrodes. In this case, we can also center the powders into compacted electrodes. With respect to particle-particle mixing, we can connect different particle generators and control their production rate so that we can achieve a desired mixing ratio in the final products. The most elegant way of creating alloys is to use the electrodes made of different materials, especially attractive for 2 materials that are immiscible in bulk. Next, I will explain to use this way to form stable alloy nanoparticles that contain the immiscible materials. In the previous slide, I already showed that the spark oscillator is within a few microseconds. Its waveform is presented here. The positive polarity part is colored as green, while the negative part is red. The polarity switch between the 2 electrodes makes the electrode take turn as the momentary cathode, which experience cation bombardment. Because the cations have greater mass and energy than electrons, the momentary cathode dominates the material vaporization. Helped by the oscillatory sparks and the subsequent shock wave, the vapors from each electrode were mixed and to perform conucleation at a very high quenching rate. The mixed clusters are then kinetically trapped and grew to alloy nanoparticles. Most importantly, the oscillatory spark determines the energy sent to each electrode, and this energy is corresponding to a specific mass vaporized. Therefore, we can predict the fading composition of electrodes as well as the composition of the final alloy nanoparticles. Through these oscillatory sparks, we successfully created many new alloys confined in the form of nanoparticles. The alloys range from binary to binary elements. For example, here, for binary alloys, they contain miscible materials such as iron, palladium, and immiscible materials such as iridium copper, platinum gold, gold tungsten, copper iron, iridium silver. Others ranged from ternary to the ternary alloys. Up to here, we show that we can use the oscillatory spark to mix the vapors and to produce alloy nanoparticles. Next, we would also like to understand the fundamental reasons behind this. Let's first look at the mixing ability at different scales. We know that the vapor atoms are always possible to be mixed, as the atoms are generally sticky to each other. From the previous slide, we already know that the particles can capture some immiscible alloys. The bulks, however, do not have this possibility to form stable alloys. This helps us to narrow down our research question to the size-dependent mixing. Let me explain in this way. We already know that the possibility of surface alloying for immiscible metals. Actually, the nanosize effect also manifests the role of the surface mixing by decreasing the cohesion energy. Atoms on a curved nanoparticle surface have fewer neighbors and bonds than those on a flat surface. Therefore, they have decreased interaction energy with the inside atoms. This energy decrease encourages surface mixing, which then propagates inside the nanoparticles. At the end, there must be a mixing depth, which we name it the threshold size in the next few slides. To directly visualize this, let's first look at the mid-gamma plot, which we call it light cone visibility diagram, because the enclosed yellow area looks very similar to the shape of the light cone. The mid-gamma theory informs us the bulk visibility in pairwise and guides the design of alloys, including high entropy alloys. The work function and electron density at the boundary of Wigner's cell describe the interfacial phenomena on the atomic scale. Therefore, the electron density or work function can be used to estimate the enthalpy effects when bringing dissimilar elements into contact. For example, let's look at the miscibility of the observer material gold with other materials here. The dashed lines classified 3 regions: inside the yellow area, outside, and on the edges. The materials on the edges have the equal enthalpy to gold, thus the mixed enthalpy is 0. The one inside the yellow area have a negative mixed enthalpy to gold, thus they are miscible with gold. The material outside the yellow area are immiscible with gold. The most important message of the plot is that one can move the crosshair in parallel to any target material. For example, here, let's position this crosshair to the material, titanium. In the previous slide, we already showed that the alloys can be captured in nanoparticles. Here, I will explain the underlying reasons based on this plot. The blue hyperbola represent the nanoscale effect and revises the miscibility. More materials are now become miscible with gold. For example, nickel was immiscible with gold in bulk form, but become miscible in nanoparticles. Of course, we can further reduce the size for broadening the neck of the light cone so that we can mix anything with anything. However, this does not mean that decreasing the particle size will always realize the formation of alloys, because a source has to be mixed first, and then the kinetic pathway also allows keeping the mixed state to the final alloys. We therefore conclude that the miscibility limits are exceeded and we can create some new alloys that have never been reported. To further explain this nanosite stabilized mixing, we develop a thermodynamic approach for distinguishing the nanoscale stability of alloys from those of the bulk miscibility. Let's take the example of bulk immiscible iridium and gold. The phase diagram of its bulk always shows the positive value of the mixing free energy. Here we choose 2 particle diameters for comparison. For the 3 nanometer particles, we see that only a very narrow range of the composition gives a negative value to the mixing free energy. For the decrease in the particle size, we can push the mixing free energy to be entirely negative. Here we choose the 1-to-1 mixing ratio because it generally requires the maximum shift of mixing free energy to the 0 value, which demands the strongest nanosite effect. The corresponding size is named as a threshold size, and below this threshold size, any mixing ratio can form thermodynamically stable alloys. Following this principle, on the right side of the slide, we plotted the threshold size of almost all the bulk immiscible materials as a function of their bulk mixing enthalpy. Similarly, this also works in ternary alloy nanoparticles, but with a much larger threshold size because of the increased entropy contribution. From this slide, we can easily distinguish the drastic differences of the phase diagrams between the nanoparticle and the bulk form. The left column represents the phase diagram of the nanoparticles. The right one corresponds to the phase diagram of the bulks. In the bulk, most regions deny the possibilities to form alloys, but not for the nanoparticle diagram. We also see that In the nanoparticle diagram, almost the entire regions have a negative value of the mixing free energy. This also tells us that the high entropy alloys may have been overlooked, which does not necessarily to be in the center region of the phase diagram, does not require equal molar ratio for mixing if nanograin exists. To extend the description of the nanosize effect to multi-component alloys, the size-bearing term contributes to a negative value to the mixing enthalpy, and it follows the form of mixing entropy. Therefore, the resulting effective temperature Tm is added to the original entropy from the bulk HEAs, expressed here. We found that this effective temperature is inversely proportional to the particle size. And this relation is very similar to the Hawking temperature and the size of the black hole. The black hole is known as a perfect mixer. Even if unmixing occurs at temperature equals to 0, the effective temperature Tm still enforces the entropy mixing in the HEAs. To quantify the contribution of Tm, we estimate that 3 nanometer particles of binary alloys already have an entropy compared to that of a bulk HEA containing 25 elements. This explains smaller nanoparticles containing immiscible alloys are required in order to avoid phase segregation, but larger particles are suitable to contain more than 3 elements for ensuring the stability. The next 2 slides will show how to control the composition of the alloy nanoparticles through manipulating the oscillatory waveforms of the spark discharge. This plot shows the spark oscillation is dependent on different electric parameters, such as capacitance and resistance. Their correlation to the oscillation can be well predicted by the above formula. Experimentally, we can use different plasma gases, thus they have different resistivity, so that we can control the spark oscillations. Use this notion, we successfully control the composition of various nanoparticles. The predictions here in the A panel are present in black and red lines, while the dots are from the ICP measurements. We see that they have some degree of consistency. The slight discrepancy here can be related to the simplifications in our model calculations. The B and the C panels also demonstrate the similarity between the measurements and the model predictions, despite their totally different visibility trends. The STM EDX measurements of individual nanoparticles at different regions also show close similarity to those measured by ICP, as shown in D and E panels. We have finished the production of alloy nanoparticles. Next, we will show you how to collect them. There are generally 4 possibilities to collect these nanoparticles suspended in gases. In this talk, I will only focus on the first and the last one. Electrostatic precipitation was used for precisely guiding our charged nanoparticles into 3D nanostructures. This process is the so-called additive manufacturing or 3D printing. The diffusion was used for collecting our nanoparticles onto a piece of carbon paper for electrocatalytic measurements. Let's first look at the electrocatalytic results. In brief, the produced alloy nanoparticles outperform most of the ones from the literature reports. The main reason is due to the clean surface and the alloying effect to promote the chemical reactions. So this is MOR. We also did some EOR and FOR measurements. For our additive manufacturing, we also downscale the feature size of the 3D nanostructures to sub 100 nanometers. And we can materialize the structures to binary alloys until scenario alloys. All these results were never achieved before. So I will explain how can we print the alloy nanostructures. Let's start from the scratch. Potential distribution above the ground. We can see here that they are presented by the dashed lines, and the electric field lines are perpendicular to the ground surface. If a person stands on the ground, the potential distribution will be slightly distorted to a shape like this. The corresponding electric field lines are then shaped to like this. Following this idea, we make different surface patterns to manipulate the electric field lines on the nanoscale. The field lines are then arranging the charged nanoparticles to a precise location and eventually build up a 3D nanostructure. We balance the two electric fields in order to control the electric field lines to form a nanoscale funnel. The two electric field lines, one is the global field and the other is the local field, that is from the deposited gas ions. The gas ions generally form dipoles to produce the electric field lines as shown on the right side. If the surface patterns are made in an array form, and then we can use the parallel electric funnels to print tens of thousands of 3D nanostructures just in one pass, which normally only take about 20 minutes. Here are the results from our new nanoscale additive manufacturing technique, which contains binary, ternary, quaternary, quinary, and scenario alloy nanostructures. This slide shows the feature size of 3D alloy nanostructures that can go down to 50 nanometers. Until here, I already showed you how to make and control the alloy nanoparticles and understand their underlying mechanisms, as well as some practical applications in electrocatalysis and a novel 3D nanoprinting. Next, I will introduce the upscaling of the nanoparticle method with two different approaches to scale up the nanoparticle production in one single unit and to enable up the unit. In one single unit, the mass production rate is proportional to the spark repetition frequency and the mass ability per spark. The green box one is fixed. In the traditional RLC circuit on the left side, it has an upper limit frequency about 300 Hz. However, higher than this frequency, the spark switches to a mode or continuous aux. Aux discharge generally generate much larger particles, about a few hundred nanometers to a few microns, and not be able to produce alloy nanoparticles. In order to still be able to produce very small particles and to have the great feature of mixing to form any alloys, we developed a switching circuit to decouple the charge and discharge cycles by adding a number of fast electronic switches. This can increase the frequency up to 25 kHz and still maintains the oscillatory feature of a single spark, which guarantees the vapor mixing and the production of very small nanoparticles. As we can see from the bottom right panel, the production rate of nanoparticles linearly increases as the frequency increases. Doing so allows us to increase the production rate by 2 orders of magnitude in one single unit. The next scaling up approach is to enable out the single unit and put the particle source in a closed loop system. These setups in the photos are from Duisburg Essen University for demonstrating the successful parallelization of 16 particle generators. To summarize, we have presented a versatile nanoparticle technology for creating alloys that have never been available before or not possible by any other method. The success is based on the vapor crystal transformations. We also developed a thermodynamic approach to fundamentally understand the mechanisms of the formation of impossible alloys. The produced alloy nanoparticles are showcased in high-performance catalysis and to a novel 3D nanoprinting technique. Therefore, we believe this platform technology will contribute to discovery of new materials, new structures, new applications, and new theories. Therefore, this can push new frontiers in many other fields, such as 3D nanoprinting, metrology, catalysts, optics, microelectronics, and 3D metal materials, etc. Last but not least, I would like to thank my funding agencies and colleagues for supporting me to work in science and which I feel very fascinated and inspired. Great thanks also go to the organizers, Professor Ludwig and Professor Schumann, for hosting this amazing online conference. Hopefully we will continue this every year. Thank all of you for your attention. If there are any remarks, comments, I'm very happy to take them.